so in the last lecture, we saw how the Max-Flow-Minkert theorem work, or basically we proved the correctness of the Fulkerson algorithm, right? That in the lecture before that, what we had done was that we showed how what was the running time and so on. And in the last lecture, we showed the correctness of the algorithm. That it, in the end, when the algorithm finishes, it actually outputs the maximum flow. And also we showed that there is a cut of the same capacity as the maximum flow, right? So we did the running time before, and then we did the correctness in the last lecture, right? But then we're talking about some things in the end. So let's, go through those, issues, let's say. So what is the running time? The running time is order MC. We had seen that. Right. And also we wanted integer values and capacities to be integers. So this for now we'll not worry about. So let's keep it the same. But let's look at the the running time, order MC. And what if and in fact, I don't know. Last time I did mention that even if for reals, the max flow is equal to min cut holds for, let's say, positive reals, okay, capacities. So this I had mentioned last time, but today we are more interested in talking about the running time. Right? Okay. So the question is, what if C is too large? If you remember in some earlier algorithm, what we had said that if this C is too large, and then the input size is in the algorithm is not running in polynomial, so not polynomial. So order MC is not polynomial in M and N, right? That is the input size. So we had this word called pseudo polynomial for these. Where this why pseudo polynomial? Because this C actually represents the capacity of of the edges and so on. Right? So the question is, what if C is too large? Then this algorithm is going to take a long time. So let's look at a bad example. When C is too large and this algorithm can take a long time. So you have, let's say, S, U, V, and T. You have these edges, all with capacity 100. You have this one edge with capacity 1. Right? So what is the max flow here? What is the max
200.
flow here?
200.
200, right? Because you can just flow 100 on the above path and 100 on the below path, right? But now what does Ford Fulkerson do? It just looks at one path in the, so initially we know that GF is equal to G. So this is G, and initially GF is equal to G. So now we look at some path here, right? So suppose we look at this path. Okay, so for this path, so first path is, let's say, SUVT. What is the bottleneck for this path? What is the bottleneck for this
One.
one? One. Right. So now what is going to be the GF? Okay, so now this is going to become 99 because we have decreased. This is going to remain 100. This is going to remain 100. This is going to become 99, the forward edge. Then we'll have a backward edge here of capacity 1, a backward edge here of capacity 1, and a backward edge here. Capacity 1. There's no forward edge here because this one is saturated now, right? So this is the GF that we get. Now in this GF, which path suppose we choose? Suppose we choose this path. The second path. SVUT. Again, what is the bottleneck? Bottleneck is 1 again, right? So again, now you'll decrease of this one and so on. So now the GF you'll get for this is going to be so now these two will become 99, all of them. And now you have this back edges, all of them having capacity 1, 4 of them. 1. And now this edge is a forward edge only because this backward edge goes away because now the F value is 0. So that's it, right? And now this is very similar to this one, the first one, in some sense, right? So basically, if you analyze this, so basically now after 2 augmentations, so what is the flow value here now in the second GF? 2, right? So after 2 augmentations, we get value of the flow to be 2, right? So it will take 200 augmentations to reach flow or max flow, which is 200. If we choose the paths like this. Right? And 200 augmentations is exactly, this is exactly C. So actually, what is capital C? Capital C is, okay, let's just remind ourselves. Capital C is summation delta plus E belongs to delta plus E. Delta plus of S, C, E, right? So you take whatever edges are coming out of S and then you sum their capacities up. That's what C is. Okay, good. Okay, so this is exactly C now. So that means it can take C many iterations, which might be very bad if C is very large, right? So we want to avoid that. We don't want it to take so many iterations. So is that clear that there are some bad cases where it can take a lot of iterations? There's another problem that I had mentioned. So still we are dealing with integers. In fact, for reals, you can't even show that the algorithm terminates because we crucially use that, okay, it increases by 1 in case of integers and the maximum is c. So after c many iterations, it's going to finish. But what if the increase, or the increase decreases, like, whatever the flow value increases by, that decreases over time. And then, you never reach that c value, or, it takes infinitely many iterations to reach there. So you can make some examples where this is possible, and so that's why we are talking about integer valued flows for now. Okay, good. So now we have this problem that okay, even for integer valued flows, the algorithm can take c many augmentations, where c is the capacity of outgoing capacity of s. Okay. So now, how do we how do we tackle this? So any ideas? I mean, how do we? What were we doing wrong in this bad example?
We are taking the wrong path.
We are taking the wrong path, right? So if we would have taken some, better path, then, like, if we would have taken just SUT, then we would have been better, right? So the idea is how to select good paths. And why was it wrong?
The cut was too small.
The cut was too small. The bottleneck was too small, right? On the path.
Yes.
Because what is the value we are going to increase by? We are going to increase the flow value by the bottleneck, right? In one augmentation. So that is the idea that, okay, to choose paths with large bottleneck. Right? And this will, hopefully will make more progress towards C. Or let's say optimum. Okay. So now you are not making a progress of 1, you are making maybe larger progress because you are choosing a path with large bottleneck, right? But we can't really, we don't look for the largest bottleneck, because that itself will take a lot of time. Finding is very time consuming. Okay. So what do we instead do? We look at a path with bottleneck which has more than, some cutoff value, right? So instead, look for paths with bottleneck capacity at least delta. Okay. Where delta is some scaling parameter. Call this scaling parameter. Not some, is scaling parameter. Let's call it. Okay. Good. And so basically what we want to select, now we want to select, paths which have bottleneck at least delta. And how do we do that? So let's define this graph GF delta, right? So subgraph of GF consisting of edges with residual capacity at least delta. Okay. So now we'll be just looking at even such graphs, and we'll only be looking at such edges where the residual capacity is at least delta. Whatever is left over is at least delta. So, but still, we have not chosen this delta. We have not, done anything till now. We are just saying that okay, this is what we are going to use in some sense. Okay, good. But now we are ready to design an algorithm. So, before I actually give the algorithm, any ideas for so the idea is that we use some cutoff. But how do we change this cutoff? How do we go about using this idea into an algorithm such that it gives faster running time? Anyone?
So we can look at all the edges out of the source in the residual graph and maybe take average of it. That's one idea.
Maybe take average of it, and take delta to be the average of that.
Yes, sir.
Okay. Take delta to be average of that. Yeah, definitely that's one idea. And then the question is, how do you? So basically, the point is going to be that okay. So let me give one strategy, and then we'll see how to implement that, and then I'll try to say it intuitively, and then we'll see that what is the actual flesh and blood things inside that strategy. Okay. So what we will do is take delta as large as possible, in some sense, and see that, okay, can we get some path with this delta? And if we get, good, right? Otherwise, we decrease the delta by half. Okay, then again we see, can we get some paths with this delta? If not, so this way the number of iterations is going to be not a lot, because first time you are, for these iterations for delta. And now for each delta also, we should not be able to get too many paths, because for larger ones we have already got, and for this one only we are going to get, right? So it's like, we have these 0 to C, right? And now we want some delta here, such that, the flow is here, we find the flow and we increase the flow by delta. So not much will be left after that, is the point, right? Then we go for delta over 2, and we have already covered the flows of size delta and above, so not many can be left for delta, and so on. So this is what we are going to try to do. Okay, so we'll take delta to be a power of 2, and then we will, we'll first look at the largest possible power of 2, which is still smaller than C, at most C, and then we'll keep making it half in each iteration. Okay, and that way, what is the number of iterations that it will go to? That will go log C iterations, because we are halving it each time. And in each iteration, now we still have to argue that how many augmenting paths we can get in each for each delta, right? So that's going to be the strategy overall. But we'll see the details in just a moment. But if there is any question about any informal question, or at intuitive level about the strategy, you can ask now.
Sir, we are basically doing a binary search for delta.
It's not a search, right? Because we are actually collecting things. Okay, so what these deltas are? These deltas are that, okay, I look at the graph with residual capacity. So we are collecting the flow in some sense. So we look at the graph with residual capacity at least delta. So we are like, okay, so imagine the pipeline example or the road example. So we see that, okay, are there, so suppose 100 is C, and then we take this delta to be 64, right, for example. So are there any, roads, or can we get from S to T with 64? And if we get 164 there, then there is only very less left after that, right? So we have already collected 64 from C in some sense. Next time we'll look for 32 and so on. And if we don't get anything of 64, then we'll argue that there cannot be many iterations and so on. So what we are trying to do, we are trying to gather larger and larger flows initially, so that the later iterations we don't repeat them too many times. So it's not exactly a search, because in searching, like, you are looking for something, but it's like collecting things. First bigger things, then like slightly smaller, such that the number of iterations is found. Does it make sense?
Yeah.
Okay, good. Thanks. Any other? Okay, so now let's look at the algorithm, right? So it's called scaling max flow. I hope I can finish it in this page. So yeah, I mean, more than the actual details, I think this idea, if you can get and somehow get it in your head that this is a strategy that can be used for minimizing the number of iterations. That is, I feel, it's more important. But anyway, let's now look at the actual algorithm. Initialize f is equal to 0 initially, right? For all e belongs to E. And then set delta is equal to 2 to the k, such that delta is still less than or equal to C. And now, while delta is at least 1, what do we do? As I said, while there exists an ST path in GF delta, right? So we start with the large delta, and what we're saying, while there exists an ST path in GF delta, so let P be such a path, a simple ST path in GF delta. Then we augment this path. We put f is equal to f prime. We put gf is equal to gf prime. Sorry, gf delta. Gf delta is equal to whatever gf prime delta now, the current delta, whatever. And then you end this while. Then you put delta is equal to delta over 2. And then when delta becomes 0, then you end this while. And then you return f. Okay. So now there are these two while loops here. So this is one while loop, right? So let's call this outer while loop. And in the book, they call it delta scaling phase, because we are scaling the delta in this. Okay. And this is the inner while loop. This is where augmentations are happening. Okay. So is at least the description of the algorithm clear? What the algorithm is trying to do? Any question about that? So what are we doing? We look at the graph, which is first, just induced by delta capacity delta, residual capacity delta edges in GF, and then we collect a flow from there. If it exists, then when no flow exists in that graph of residual capacity delta, Then we go down, we decrease our delta, and then we look at the residual graph and look at the flow there. We collect those and so on. Okay, any questions?
Then how much time will it take to determine if there are paths which have at least delta bottleneck or not?
That is easy, no? Because you can just, so what you do, you have whatever representation of the graph and you have the capacities, and you just delete the edges which don't have that much capacity, delta capacity, right?
Okay, so okay, got it.
So that can be done in order m time. And then you do a BFS, DFS, whatever, again order m time, you can find the path. Okay. We'll do a running time analysis, but yeah, I mean, that part is not very hard. Okay. Any other question? Okay, good. So let's now try to analyze this algorithm, right? So let's first do correctness analysis, which will be easier. So basically now when delta is equal to 1, so first thing is that, it always remains integers, right? So you can show that the flow remains integer. At all time, right? And now finally we have, when delta is equal to 1, then we have GF delta, basically flow remains integer at all times. So residual capacities also remain integer at all times and so on. So GF delta is equal to basically GF, right? So finally, when the algorithm will stop, that means there is no ST path. That means when the algorithm terminates, it returns the maximum flow. Why? Because, for that particular GF, you can show that, there exists a cut, such that, it has exactly the capacity of value of F, just like previous, just like we showed the correctness of the original, right? Maximum flow. So correctness is actually, I'm not going to go into detail. That's very easy to see, given you know how to show correctness of fold filters. Okay. So let's now look at the running time. Okay. So now let's just look at the inner loop first and how much time the algorithm takes in the inner loop. So each iteration of inner loop, we have to find, again, whether there exists an ST path in GF delta. As I said, order m time to find path in GF delta. Again, order m time to augment and to get new GF delta to get F prime and to get GF delta. So this is fine. So total order m time inside the loop for each augmentation. Because if you see there is nothing else happening, there you need to find a path, then let P be such a path, then you augment it, and then you define the new GIF. Right? So that's fine. Basically, now we just need to figure out how many times these while loops get executed, right? So now let's fix delta. let's fix the outer while loop. So let's fix an iteration of outer while loop for delta is equal to delta. Okay, so like, just the current value of delta is delta here. Okay, so might be abuse of notation, but you get what I mean, right? Okay. And okay, all right. And now we want to see, but okay, before that, actually, let's do something. Okay, I should not have erased that. I should just keep it for later. Actually. So this is going to be the analysis for inner while loop, how many times the inner while loop is going to run. But let's look at how many times the outer while loop is going to run. Because that's going to be easier. So let's get it out of the way. Any ideas? How many times the outer while loop will run? I've already
log C.
log C. Order log C. I mean, so we have this as I had drawn this. Somewhere here is C. This is some C over 2. Somewhere in between is this whatever 2 to the k is equal to delta that we had put, and then basically in each iteration it comes to delta over 2, then delta over 4, and so on. So there are going to be whatever 1 plus log 2 base C, many iterations maybe. So it should be here. So basically order log C. Why? Because it halves each time. So at most the number of iterations it's going to take is order log C. So that is not very hard. So good. It's good to get that out of the way. So this happens order log C, many iterations. If that is not clear to anybody, please ask. Okay. But the inner one is the one more interesting. Okay, so for that, let's fix that. Okay, now we have fixed some delta. And now we want that how many times this augmentation can happen. Okay. So we want to know how many times augmentation can happen. Right. So that is the question we want to ask. And what is the observation? Every time the inner while loop runs, the flow increases by delta. Right? Why? Because you anyway you are looking at a path in GF delta. And what does that mean? That, the bottleneck is going to be at least delta. So you increase the, capacity by, increase the flow by at least delta. Right? Good. So now the key lemma that we are going to show is that after, an iteration of the outer while loop has finished for some delta, then how much closer we are to the actual flow, actual maximum flow. Okay, so that we are very close actually. There is not much left. Okay, so let's say that let F be the flow at the end of an iteration of outer while loop with value delta. Okay. Then there is an ST cut AB. such that capacity of the cut is less than or equal to value of F plus M delta. Okay. That means, and where M is, of course, M is equal to number of edges, right? G. So capacity of AB, and what does that mean? Which implies, can we say something about the now the maximum cut? Sorry, maximum flow. What is the value of maximum flow now? At most the cut, right? Which is value of F plus. Okay. So we are already close to the maximum flow. Whatever F we have is already close to the maximum flow plus M delta, right? It does not depend really on C. It only depends on delta. Okay. And why can we say that? Because any the maximum flow, its value is going to be less than any cut. I mean, not less than, at most any cut. So now we give a cut with this much value, that means the maximum flow cannot have more than that value, right? Okay. So let's quickly like now show this lemma. And this lemma is actually, again, now we want to get, a cut. And just like, find an ST cut just like we did for Ford-Fulkerson, right? ST cut. And what? Let again, A is equal to set of vertices reachable from S in GF delta, and B is equal to whatever we want to say. Okay. And now, so okay, so this is A, this is B, here is S, here is T. So clearly AB is an ST cut, right? Because otherwise there would be a path. Just a moment, sorry. Yeah. So, what I was saying that AB is an ST cut because otherwise there would be a path in GF delta, right? Which would mean that, the while loop would not terminate. Inner while loop would not terminate. So we would not reach the end of an outer while loop, right? Right. So this is an ST cut just for sanity check. Now what we want to show again is that we want to relate the value of the flow with capacity of this cut. And the obvious way to do that is, look at edges. So let's look at this edge E, UV, such that it goes out of A. And let's look at an edge E prime, let's say, is U prime, V prime, which comes inside A. Okay. So, and what can we say? So claim 1 is CE is less than or equal to FE plus delta. And why is that the case? Why should that be the case?
Otherwise, if C is greater than Fe plus delta, then C minus Fe is greater than delta. So there would be a ST path in. the residual graph.
There will be an edge, a forward edge with the residual capacity at least delta. Otherwise, if C is greater than Fe plus delta, then C would have, or E would have, residual capacity at least delta. So belongs to E belongs to whatever GF delta, and that contradiction to definition of A and B. Because then why did we not include E? Because if U was reachable, then V also has to be reachable, so we should be in A. Okay. So contradiction to definition of A and B. Good. Now claim 2. So basically what did we do in claim 1? We said that this edge is almost saturated by the F except delta. Whatever is left is delta, right? And for the backward edges, we are going to say that, they are not carrying too much. So F of E prime is at most delta. And why is this true? F of E prime is at most delta or strictly less than delta.
Otherwise, it would have a backward edge, which would again make a path from S to T.
Exactly. Otherwise, if F of E is greater than or equal to delta, then there would be a backward edge. With residual capacity at least delta. And the same thing. Contradiction. The same contradiction you get here, right? So here you would have had an edge here, and the same edge would have had capacity more, and so on. So these things we get that, okay, the outgoing edges are almost, saturated by the flow value except delta, and the coming back edges are, have flow value at most delta anyway, right? So now this is easy. So for all, now we know that for all E belonging to delta plus A, CE is less than or equal to F of E plus delta. And for all E belonging to delta minus A, we have F of E is less than delta, right? And now we just apply our formula that we had. VF is equal to summation E belongs to delta plus A, F of E minus E belongs to delta minus A. This formula we showed in the last lecture. F of E, right? So whatever is going out minus whatever is coming in is the value of the flow. Okay, so this is very intuitive, but like we have shown this formally in the last lecture. And now we know the value of Fe is at least, C minus delta from this. So C E minus delta, E belongs to delta plus A. And the value of Fe is at most, or so actually this can be strictly greater, right? Anyway, it doesn't. Summation delta E belongs to delta minus A, right? And this basically we get then is equal to summation CE, E belongs to delta plus A. So this we get from here, and this we get from here. Minus E belongs to delta plus A delta minus E belongs to delta minus A delta, right? And what is this? This is the capacity of the cut, this value. C less than equal to CAP minus delta M or M delta, right? Because these two are different edges. So of course, even if it contains all the edges, then it is M delta, right? So V of F is less than or equal to this, or CAB is less than or equal to VF plus M, right? This is what we wanted to show for the lemma. Lemma said that CAB is less than or equal to VF plus M delta, and that's what we have shown. That C of AB is less than or equal to VF plus M delta, and that means that the maximum flow is less than or equal to, so max flow is also less than or equal to VF plus M delta, right? And now we can show how many times the while loop runs.
So C of VAB is greater than or equal to VF plus delta.
C of AB, okay, yes, you are right. Thank you. So that is why it should be this.
No, sir, it was right.
Was it?
The last
Yes,
step, the inequality you
yes.
changed.
Did I? Okay, fine. Here, right?
Yes, sir.
This one. Yeah, good. Okay, yes. Yeah, so max flow is going to be less than or equal to VF plus M delta. Okay, good. So now can we get bound on the number of how many times the inner while loop runs? So for a fixed value of delta in outer while loop, the inner while loop runs at most 2m times. Sorry. Okay, so this is what we want to show, that it runs at most 2m times, and basically now we are getting this number independent of C. And the proof is by induction. So for first delta already, we have each edge out of S, for delta is equal to 2 to the k, the first iteration. So for that, each edge outside S can be in delta plus S can be augmented at most once, right? So this is true for the first iteration. And now let's say that look at some iteration of the while loop. Outer while loop with value delta, right? And let FP be the flow at the end of previous while loop. Right? And what is the previous while loop? With delta prime is equal to 2 delta. That was the previous while loop, right? So let's take that delta prime, right? In the previous iteration, okay? And let the maximum flow be F star. So basically what we have shown here is that after this, not much is left. M delta is left, right? So that's what we are going to use now. So we know that value of F star is less than or equal to value of FP, whatever we had got in the last iteration, plus M delta prime. And delta prime and delta don't differ by too much, right? Less than or equal to V of FP plus 2M delta prime, 2M delta, right? They differ by just a factor of 2. And now this we have already got already got after previous while loop. And this, is the maximum that is possible. And we know that each augmentation increases the value of flow by delta, right? So now, and maximum, what we are left with, so here there is C, here there is V of Fp, not even C, like V of F star. And here we are already there, V of Fp. And what is left? Left is 2m delta. And in each iteration, we make delta jump. So how many iterations of the inner while loop there can be? 2m iterations, right? So at most 2m iterations of inner while loop. Right? So this finishes the proof now. So what is the total running time now? Anyone?
N log C.
No, there is another m.
M square log
And
delta.
m squared log delta log c, right? Log delta is going to be log c. I mean, delta is variable, but the first delta that you get is log c. I mean, first delta that you get is between c over 2 and c. So log delta is going to be equal to log c, approximately. Right? So total running time, I leave it to you. Order m square log c. So this is m for augmentation. Each augmentation in inner while loop, m for number of times inner while loop runs, and this is for number of times outer while loop runs. Log c. Right. So you can figure it out, but this is order m square log c. Okay. Good. So this is actually, so I'll just say two things. So this is actually better. So this might look worse. So earlier we had order MC, and now we have order m square log c, right? So this can be better if c is too large. But if c is small, if c is, comparable to m, then this is better. But there is something nice about this algorithm is that now this is not pseudo polynomial. Why? Because if you have a number, let's say 2 to the 100, if suppose some C was 2 to the 100, some capacity, some CE, then representation takes only 100 bits. Right? That means this is now order m square log C is actually polynomial in the input size. Because you have to also give the capacities as input, right? And to represent a capacity C, you need at least log C bits, right? So this is like in true sense polynomial in the input size. But this one was not as we saw, because this is like what we called pseudo polynomial. Because this is number of digits in C. Log C is number of digits needed to represent C. Right? But still there can be a question which can be asked, that whether we can just get rid of dependence on C altogether. That is algorithm in polynomial in M and N. And that is the question actually which has been explored a lot, and it has a positive answer that we actually have algorithms which run in polynomial time in M and N, and we'll explore one of those in the next 1 or 2 lectures, which is called the pre-flow push algorithm. Okay. So any questions about today's algorithm, the scaling algorithm or whatever? We are over time, but I can take 1 or 2 quick questions if there are any. So basically the idea was that, okay, we have the final capacity, whatever, we take, these residual graphs sort of, with higher and higher capacities, then find the flows there, collect them. Then, we try to go towards lower capacities and so on. And by this, we decrease the number of iterations. I mean, the details are, there and they are necessary, but the basic idea of the algorithm is this. Okay. Any questions?
So the integer capacities only are considered, right?
Yeah, we are still considering integer capacities. That's correct. We'll see. I mean, I'm not sure whether we'll deal with the real capacities. We'll get time to do that, but we are still considering integer capacities. You're right. I mean, if you're interested, there is a discussion in the book about how to relax those things and so on, and I would encourage you to go have a look. Any other question? Okay. So if not, thank you for coming, and see you tomorrow.